Hey guys, welcome to day 2 of chapter 2. This is section 2.2 about polynomial functions. Polynomial functions is a generalization of what we did last time. Last class, remember we did quadratic functions. Quadratic functions are just a special case of polynomial functions. So here's what we're learning today. Number 1, properties of functions that are polynomials and their graphs. And then number 2, how to determine the end behavior. In other words, what happens when x gets towards negative infinity or positive infinity. Number 3, how to find the zeros by factoring, also called the roots. Number 4, how to identify the relationship between the degrees of the polynomial, the number of real zeros, and then turning points. We'll talk about what turning points are. And then finally, how to graph the polynomial functions. And we've done a little bit of that with we've seen some polynomials with like x squared and x cubed, and also lines. Lines qualify as polynomials as well. All right, let's start with learning the properties of polynomial functions. So first of all, what is a polynomial function? A polynomial function degree n has this form. Don't be intimidated, guys, by the mathy look of this. It's actually much simpler than it looks like. They're just trying to be general because we want to allow for the different possible numbers. So it has like a sub n, just a representation of some number that's a coefficient of your x to the nth power. X to the nth power is whatever the highest degree in your polynomial is. So just like a simple example, let's say n is 5. You could have something x to the 5th, x to the 4th, x to the 3rd, x squared, x to the first power, right? And then some coefficients for each. So maybe a sub the n could be like 7. And these could be either plus or minus. I'm just picking random numbers, and then a number at the end, right? That number at the end, we call a sub 0 because, just matching the powers, right? X is really x to the 1. So a sub 2, x to the 2, a sub n minus 1 for n minus 1. This is just a generalization to show you, okay, polynomial, you've got a bunch of x terms and different powers of the x's, and each one has a coefficient. You remember last time when we did quadratic functions, we said the first term shouldn't be 0. Well, same thing applies here. If it's going to be a degree n polynomial, then that first term should not be 0. Otherwise, you wouldn't call it a degree n polynomial. You'd say whatever the next highest number that has a non-zero coefficient is. Right? If it's 0, then that first thing would disappear. Okay, sometimes, the polynomial functions might not look exactly like this when you first see them, but you'd be able to expand them out. Just expanding means just multiply everything together. And if you're to do that, then you'd end up with something that turns out to look like that. So that's the characteristic of a polynomial function. If you're able to multiply it out and it has this format, then it's a polynomial function. Okay, what do we know about polynomial functions? I'll let you read this other part afterwards, but what do we know about them? First of all, their domain is everything. So the domain of a polynomial function is all real numbers, negative infinity to positive infinity. You can plug anything into it and it will give you some real value. And secondly, the graph is smooth and continuous. I like to think of this as like a polynomial. It's kind of like a wet noodle. So it has some kind of shape like this. We've seen before, you could lay out your noodle as a straight line, I guess it's like a dry noodle, I guess. Or if it's like a quadratic function, you can just lay your noodle out with one bend or like this, right? Or if it's like a cubic, you could lay it out like this. Basically, any kind of squiggle, as long as it doesn't have any corners or cusps. Corners would be something like an absolute value has, like that kind of sharp corner. Or cusp is something like it's also a sharp thing, but curved going into that sharp point. And the other thing is it has no gaps, right? It has no gaps. And that's no gaps is part of it being having a domain of negative infinity to positive infinity. So you could have something like this. That would not be a polynomial. Or something like this where it has any kind of jump or something. Okay, all right, let's try questions 1 through 4. These are the first easy questions. Okay, number 1, state whether or not the function is polynomial, and if it is, find its degree. Oh, okay, so actually a little more to it. Find the degree, leading term, and leading coefficient. So number 1 through 3 are actually super easy. Number 1, is that a polynomial? Yeah, it's a polynomial. This would be like the a sub n right here, right? X to the n, where n would be 8 in this case. This would be a sub n minus 2 because there's no x to the 7th, x to the n minus 2. Anyways, that's how it matches up with the definition. But yeah, all these terms, right? They're what do you call? expressions in terms of x or some power of x or a constant. So yeah, that checks out. Okay, what is the leading term? Leading term, oh, sorry, degree first. Degree, I'm just writing the answer right here because it's easy. Degree is n. Leading term is this guy right here. And the leading coefficient, coef for short, is -7. Yeah, it's just the term of that guy. Okay, that's easy. That's number one. Okay, number two. F of x is x minus 1, where x is between -10 and +10. So this one, x minus 1 by itself, that is a polynomial. It satisfies the definition, right? It satisfies the form. But you have this restriction on what x could be, which disqualifies it from being a polynomial. So that means no, it's not a polynomial. Not a polynomial function. Because of this restriction, right? X should be allowed to be anything. Okay, number 3. Did I say number 2 or 3? Okay, that was number 2. Number 3. Number 3. Is that a polynomial function? The answer is no, because you're dividing by this guy. And because you're dividing by that guy, that means x cannot be -1, because then you'd be dividing by a 0, and that would be a bad thing. The universe implodes. So it has a domain restriction, right? Now, one thing to note here, guys, if you're to simplify this, x squared minus 1 is actually x plus 1, x minus 1. And so you could cancel, right? And so you'd say, oh, isn't that equal to x minus 1? Well, it is, but you have this one caveat, which is that x cannot be -1, right? And then that makes the denominator 0. So it's almost the same as x minus 1, except it cannot be where x is equal to -1. And so because of that domain restriction, this thing is not a polynomial. The domain should be free to be, x should be free to be whatever you want. So not polynomial. Okay, last one. Okay, last one. It doesn't look like the format of a polynomial, right? But it actually is, because if you're to multiply all these things out, then the result would be something that looks more like that, right? And then that would be a polynomial. So it's okay. That is a polynomial. Now, how do you find the leading term and leading degree? Okay, so this case, you could multiply all this stuff out. You'd have to FOIL this piece because it's squared, multiply the result by 2x plus 1, and then multiply that by 4 minus x. But that's pretty like troublesome, right? So there's a little trick around this. What you can do is just look at all the x terms. So here there's an x term, right? And combine that with a square. So that gives you an x squared. And then here there's a 2x. Okay, so that's a 2x term. And then over here is a -x. So it's a -x term. And what you do is just multiply those terms together. That's going to skip ahead right to the end of the leading coefficient. It's going to give you it's going to take you all the way to the leading coefficient. So that would be multiplying those first two pieces. That's 2x to the third. And then you multiply by the last x, it's going to give you -2x to the fourth. So that's your leading term. And the leading coefficient is the number in front. So the -2 would be the leading coefficient. Okay. -2 is the leading coefficient. -2x to the fourth is the leading term. Okay, that's it. Problems 1 through 4. All right. In this video, because we have kind of a lot to cover in the other videos, and I want to try to stick to 4 videos, we're going to cover the second topic in this video as well. So if you want to pause and take a break before I jump in, though, then feel free to do so. Okay, second topic. Second topic is determining the end behavior of a polynomial function. End behavior just means what happens when x goes way to the left as it approaches -infinity, or way to the right as it approaches positive infinity. So that's -infinity, x goes that way to the left, or positive infinity, x goes that way to the right. Okay, so there's 4 possibilities, and the 4 possibilities for the end behavior of a polynomial function are determined by the leading term of the polynomial. So for that reason, we call the 4 possibilities together the leading term test. Okay, we're going to focus in on that leading term, which we spent a little time just now finding, right? We found the leading term. Okay, so case number 1, you have an odd degree polynomial, and you got a positive lead coefficient. Odd degree means something like here in this example, you have x to the third. The 3 is the odd part, right? Oops, didn't mean to do that. 3 is that odd part. And here it's a positive lead coefficient. Yeah, positive, not negative. So what do we know about this? Okay, this is basically like x to the cube, x cubed, right? So what does the graph look like? It's same as x cubed, except with the 5, that just means it's stretched upwards. So it has like this shape, right? So what happens as x goes to the left, notice that you're going down, right? And as x goes to the right, notice you're going up, right? So far out to the left, you can exaggerate this a little bit just to kind of see what's happening. Far out to the left, this thing is going down, and far to the right is going up. Okay, next case is you have an odd degree polynomial, like 3, x to the third, and this time you have a negative coefficient. Well, what does that do? It just switches it around, right? So you get this is like negative x cubed. 5 just makes it stretchier up and down. But as you go to the left, it's going up, and as you go to the right, it's going down. Okay. Now, even degree polynomial, that's something like x squared, right? You might have a number in front, like 5, that just makes it more dramatic. Even degree, positive number in front means it opens like a parabola, right? Essentially like a parabola. Now, right now, we're only concerned about the ends. So this is actually true no matter what power. This could be a 4 or a 6. Anything that's even, it's always going to follow this pattern. Okay, so the pattern is up to the left, up to the right. So this is up and up, yeah? As you go far to the left, far to the right. And then, if you have a negative of an even power, then the even power here and a negative in the front, then it's going to do the opposite, right? It's going to go, we know from experience, that's an upside down parabola. What happens with an upside down parabola? It goes down as you go to the left, and it goes down as you go to the right. Okay, so this looks like a lot to remember, right? But really, you shouldn't be trying to memorize this thing so much as just understand what's happening. So don't think of it as rules to memorize, even though I kind of just presented it that way. But try to just make sense of it. Think about what happens with a polynomial. With a polynomial, right? Like let's just give an example real quick. Let's use this 5x to the third minus 2x squared plus 100x minus 100, 1,000, let's say 10,000. As x gets really big, this guy overpowers the rest. So basically, you can ignore all these guys and only focus in on what happens here, because as x gets super large, like think of x as being like a trillion. A trillion cubed is going to be way more than anything squared, even if it's multiplied by a big number, or even bigger than trillion, quazillion, quintillion, whatever. So yeah, this guy is gonna overpower everything else basically, and so the end behavior is gonna look like this leading coefficient, right? And so if this x cubed is a negative number, that's gonna be negative overall. If you multiply that by a positive number, overall it's gonna be negative, and so that follows this pattern going down, right? So you can kind of make sense of it that way. Now, if you rather just remember a quick representation for each type, you can think of it that way as well. Just think about the x cubed, negative x cubed, x squared, or negative x squared. Those would be like your representation functions for each. All right, so let's jump into the questions now. Just doing 2, 5, and 6. And we're given 2 polynomials, and we're going to discuss their end behavior. Let's cut and paste these guys this time. Let's move this down. Okay, start a new page for me, please. Thank you. Okay, so here, let's take this first polynomial, number 5. Okay, I'm doing number 5 here. And I want to know the end behavior, right? So first thing I do is just ignore all the other pieces of the polynomial that aren't the leading term. So ignore all those guys. They're going to become unimportant as x gets really large. So I'm only focused on this thing. Notice I have a positive number in the front and I have an odd power, x to the 7th. That means as x goes to negative infinity, this x to the 7th is going to be negative. Multiplied by a positive number is going to be negative. So y is going towards negative infinity. Okay, as x goes to positive infinity, x to the 7th is positive. Multiplied by a positive number, it's going to be positive. So y is equal to positive infinity. Or y approaches positive infinity. So you notice, even though I gave you all those rules, in the end, I didn't even really use the rules. I just kind of reasoned myself through it. What would happen as x gets really big, negative infinity or positive, towards negative infinity or positive infinity. Okay, I kind of forgot to mention this notation here. This is just to tell you x is getting closer and closer to that number. So as x approaches that number, or y is going to approach this number. So as x approaches that number, y is going to approach that number. As x approaches that number, y is going to approach that number. Okay, I think I can just do 6 right here. I can fit it in. Actually, it's really easy. So same procedure. First thing I'm going to note, the highest power is 4, right? X to the 4. So ignore all these guys. I don't need them. I'm only going to zero in on this leading term, negative 4x to the 4th. So what happens as x goes to negative infinity, x to the 4th, that's going to be positive no matter what, right? Because negative times a negative times a negative times a negative, we've got 4 of them. It's going to be positive. But then I multiply that positive number by negative 4, so it's going to be overall negative. So y is going to go to negative infinity. Or the other way you can think about this is going to have similar behavior to negative x squared, right? You got a negative in front, and you got a even term. So I know that looks something like this. Okay, so as x goes to positive infinity, thinking about this here, y is also going to go to negative infinity, right? Or if you want to think of it in terms of that particular value, here, you got positive infinity, something going towards positive infinity. If I take to the 4th, still positive, then multiply by the negative 4, it's going to turn negative. So there you go. So as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to negative infinity as well. Okay, there you have it. That's end behavior. That's how we deal with it. We just focus on the leading coefficient. Just think about what happens when x gets really big for that leading coefficient. All right, guys. See you in the next video.